ever get that feeling? Like you just want to dive into something, something really mind-blowing without needing to, like, go back to school for it.
Yeah, totally.
Well, that's what we're all about here on the Deep Dive. Your shortcut to understanding the stuff that really, really makes you think. And today, buckle up, because we're going deep, deep into quantum physics.
That's right. Get ready to have your mind bent a little, maybe even a lot. We're talking about the science of the super tiny, the world where the rules of, well, everything, seem to kind of just disappear.
Poof, gone.
Exactly. Like, imagine a world where things aren't really there in the way we think of there, where, like, your coffee mug is more like a fuzzy cloud of possibilities, not a solid object.
Whoa, my coffee mug is a fuzzy cloud.
That's trippy.
It is, and it gets even weirder. We're talking particles being in multiple places at once, time getting all bendy.
Hold on, like, my phone could be on my desk and in my bag at the same time.
Basically.
Yeah.
And get this, just by looking at something, you might change what it is.
No way. That's like some serious magic. It's quantum magic. And the crazy thing is, it's not magic, it's real.
So how did we even figure all this out?
Well, that's what we're diving into today. Our sources, like a whole collection of writings about this quantum revolution, they show us how this mind-bending field came to be.
It's a wild ride, believe me. So let's get started, shall we? Let's set the stage. For a long, long time, we had this thing called classical physics, right? It was like the king of science.
Totally. Think Isaac Newton, right? Gravity, motion, the laws that pretty much ran the universe. Drop something, it falls, predictable. Light a fire, you get heat and light. Everything made sense.
Like a perfectly oiled machine, the universe.
Yeah. And the big idea was determinism. If you knew everything about, like, every single particle right now, you could predict the entire future.
The ultimate crystal ball. So what happened? When did things start getting quantum?
Well, light was one of the first clues that something was up.
Light? You mean like from the sun?
Yeah. For ages, scientists argued about what light actually was. Was it made of tiny particles? Or was it like a wave rippling through space?
Like waves on the ocean.
Exactly. Newton thought it was particles, but then this guy, Thomas Young, he did this experiment called the double-slit experiment.
Oh, yeah, I've heard of that.
It showed that light could create these interference patterns, like when waves overlap and make some spots brighter and others darker.
That sounds like wave behavior for sure. Case closed, right?
Not quite. Then we had another problem, this time with, well, hot things. You see, classical physics predicted that when something gets hot, it should release energy as light of all frequencies.
Okay, makes sense. Things glow when they heat up.
Right. But the math said that at higher frequencies, like ultraviolet light, the energy should become infinite. They called it the ultraviolet catastrophe.
Catastrophe. Sounds bad.
Yeah, it was a big problem because, well, hot things don't just explode with infinite energy.
Thankfully not. So what saved us from the ultraviolet apocalypse?
Max Planck came along in 1900. He proposed this radical idea. Energy isn't released continuously, but in tiny packets, little bundles he called quanta.
Quanta.
Yeah, like the smallest possible unit of energy. Now, get this. Planck himself thought this was just a math trick, a way to make the equations work, not a real thing about the universe.
Wow, talk about underselling your discovery.
Yeah.
So who took this math trick and ran with it?
Albert Einstein. Who else? A few years later, he used Planck's quanta to explain another mystery, the photoelectric effect. This is where you shine light on metal, and it knocks electrons loose.
Okay, I'm following.
Now, classical physics said that brighter light, meaning more intense light, should give those electrons more energy, right? More light, more energy. Simple.
Makes sense to me.
But that's not what happened. Turns out the frequency of the light, like its color, mattered way more than how bright it was. If the light's frequency was too low, even a super bright light wouldn't budge the electrons.
Huh. So it's not about how hard you hit it, but what you hit it with.
Exactly. Einstein realized that light itself was made of those little packets of energy, Planck's quanta, which he called photons, and the energy of each photon depended on the light's frequency. So higher frequency light, like blue light, has more energetic photons than lower frequency light, like red light.
So a dim blue light could knock electrons loose while a super bright red light couldn't. Weird.
Exactly. Einstein's work showed that light was both a wave and a particle. This blew everyone's minds and earned him a Nobel Prize.
A Nobel Prize for showing that light has a split personality. This quantum world is getting stranger by the minute. Where do we go from here?
Well, next we have to talk about atoms. You see, scientists knew that atoms had a nucleus, like a tiny sun, with electrons orbiting around it like planets.
Okay, the basic model of an atom.
Right, but here's the problem. According to the classical physics, those electrons should constantly be losing energy and spiraling into the nucleus.
Like a satellite crashing to Earth.
Yeah, but atoms are stable, right? We're made of atoms and we're not collapsing, so something was wrong with the classical picture.
Clearly. So how did they fix this atomic crisis?
Niels Bohr stepped in 1913 with a radical idea. He said electrons can't just orbit anywhere. They have to occupy specific energy levels, kind of like steps on a staircase.
So electrons are stuck on these specific steps around the nucleus.
Right. They can jump between these energy levels, but only by absorbing or releasing a specific amount of energy, a quantum of energy. When an electron jumps down a level, it releases a photon of light with a very specific frequency, which is why different elements glow with different colors when you heat them up.
So the colors we see are literally electrons jumping between these energy levels. That's amazing.
It is. And this was just the beginning. In the 1920s, quantum mechanics really took off. We had Werner Heisenberg, who came up with the uncertainty principle.
The uncertainty principle. Sounds ominous.
It is, in a way. It says that you can never perfectly know both the position and momentum of a particle at the same time. The more accurately you know one, the less you can know the other. It's not a limit of our technology. It's a fundamental rule of the universe.
So it's not just that we can't measure both perfectly, it's that they don't even have both values at the same time. That's wild.
I know, right? And then there was Erwin Schrödinger, who came up with his famous wave equation. It described particles not as tiny balls, but as waves of probability. This means a particle exists in a superposition of states, meaning it's kind of in all possible places at once until you measure it.
Wait, so it's like Schrödinger's cat, both alive and dead, until you open the box.
Exactly. The act of measuring forces the particle to choose one state, but before that, it's in all of them at the same time.
Okay, my brain is melting a little.
I told you it gets weird. And remember the double-slit experiment we talked about earlier? Well, someone tried it with electrons, and guess what? Same result. They act like waves, going through both slits at once until you try to observe them. Then, poof, they act like particles going through only one slit.
So just by looking, we change reality. That's some serious observer effect.
It is. It raises some deep questions about what reality even is. Is it fixed and definite, or do we play a role in shaping it with our observations?
Mind blown. And we're not even done yet, right? There's more weirdness where that came from.
Oh yeah, much more. There's quantum tunneling, where particles can basically teleport through barriers, even if they don't have enough energy to do so classically. And then there's entanglement, where two particles are linked no matter how far apart they are, so that measuring one instantly affects the other. Einstein called it spooky action at a distance.
Spooky is right. It's like they have some secret communication channel that defies the laws of physics. So how did scientists wrap their heads around all of this? I mean, the idea of something being both a wave and a particle seems impossible.
Oh, it definitely caused a huge stir. Many scientists were incredibly skeptical. How could something be spread out like a wave and also localized like a particle? It just didn't fit with the traditional ways of thinking about the world. It took a lot of time, experiments, and debates before these ideas started to gain acceptance. It required a complete shift in how they viewed reality, and even today, there's still a lot we don't fully understand.
It's like the universe is playing by its own set of rules. But here's the crazy thing. All this weirdness, it's not just some abstract theory, it's actually super practical, right?
Absolutely. Quantum mechanics is the backbone of so much modern technology. Lasers, semiconductors, even the potential for insanely powerful quantum computers all rely on our understanding of these bizarre quantum phenomena.
So the stuff that seems like science fiction is actually powering our everyday lives. That's wild.
It is. Quantum mechanics changed everything. We went from a universe that was like a predictable clockwork machine to one that's ruled by probability and uncertainty. It's a universe where the observer plays a role, and there are limits to what we can know for sure.
It's almost humbling, right? To realize that the universe is fundamentally weirder than we ever imagined. And we're still left with these huge questions. What does it really mean for a particle to be in multiple states at once? How does quantum mechanics fit with Einstein's theory of relativity, which explains gravity and the large-scale universe? And the biggest question of all, does reality exist if we're not looking at it?
These are the mysteries that still keep physicists up at night. It's been a long journey, from those first hints that classical physics wasn't the whole story, to the development of quantum mechanics. And it's all been driven by experiments that forced us to rethink our most basic assumptions about how the universe works.
So we've gone from a clockwork universe to a quantum universe, where things are fuzzy and uncertain until we look at them. It's mind-blowing, to say the least.
It really is. And for you, our listeners, I hope this deep dive has given you some aha moments and maybe even sparked some new questions.
It definitely has for me. And it makes you think, right? If reality isn't fixed until we observe it, what does that mean for us, for our place in the universe? Do we have more power than we realize to shape our own reality?
That's a great question to ponder. And here's another one. If we've come so far in just over a century uncovering these mind-boggling quantum secrets and using them to build incredible technology, what other seemingly impossible things might we discover in the future? What other mysteries of the quantum realm are waiting to be unlocked? It's an exciting time to be alive and curious about the universe.
Absolutely. And on that note, we'll leave you to ponder those questions. Thanks for joining us on this deep dive into the quantum world.
Until next time.